Hey, Professor.
Okay.
Say hi to Barb.
Hey, Barb.
We will continue with the conclusions in metric space. Here is the definition and some notations in metric space. First, this notation denotes a ball of radius r, center and A. They call it VAR here. So that is the element x in the given set of elements x, we call it the metric space, such that the distance between x and A is less than r. Okay. And in Rn, this is the usual ball of radius r. So this is the center A, and then every point that has distance to A as r, okay, is inside this ball, right? So the distance between the point and A is less than r. That is inside the ball.
Is that a three-dimensional metric space?
Yeah, in three-dimensional R3, right? This is a ball, the set inside the ball, the element inside the ball.
In R1, it would be more like a.
In R1, it's more like an interval center at A. So this is in
R2,
in
it's a
R3.
circle.
Okay. And in R2, okay, first, and then in R2,
It's a circle.
a circle, A, right? And then you have R, so that the distance between A and R is less than A, so which is inside of the circle. And then this is the inside of the ball. And then in R1, this is A, this distance is R, right? Distance is R, so everything inside this interval here.
And it's also, it could be in like R4, R5, R6, right? You could also technically have like R4, R5, or 6, but you can't try it.
Yes, technically, yes. And this is in general a metric space, right? So given the metric space, so here given a metric space, this is X, we have a pair, right? First, the collection of points, we call it X, and then there is a function, we call it the distance, or the matrix that is defined, which is satisfied by three properties. In particular, the triangle inequality that D satisfied. And in this metric space, in general, we call this the ball of radius R, center at A. Okay. Yeah. And then we define the so-called natural topology. So here is definition. We generalize all this, the concept in Rn in Euclidean space to the metric space. So here is definition 5.2.4. So that is on a metric space X, the pair X and D, right, XD, the natural topology. We say that we call this the natural topology. What is the natural topology? Actually, you can think this as the collection of open set. Okay. We thought as the collection of all the open set, and then we call it this D. Okay. So that is also called topology. Is also called topology. Associated with the matrix, okay, with the so-called or induced by, okay, or induced by D, this D, the matrix D. D is the way to measure the distance between the 2 points. Okay. Is given by the following rules. So here is given by the following. This is just a generalization of the open set in the Euclidean space in the following rule. What is it? If A belongs to this T of D topology induced by D, okay, TD. So if A belongs to DD, you think it as an open set, okay. Then what? In Euclidean space, we know that there is a ball contained in the open set, right? So that is if and only if for any X belongs to A, right? So we can find an open ball. There exists a R such that the ball of radius R center at the X. There is a column AR. The ball of radius R center at the X is contained in A. Now let me explain in the word of the Euclidean space, say well, in 2 dimensions, right? In 2 dimensions, you think of this A as an open set. So A belongs to B, you think A as an open set. So here in R2 or in R1, okay. Every open set, so here in Cal 1 advanced Cal 1, you learn R2, open set in R2 or just R1. Introduce, the professor introduced the concept of open set in R2. Just in R1.
Yeah, I think we just talked about open
It's
set.
just the real number.
Yeah.
In R1, so let's just talk about R1 and then generalize to R2.
Yeah.
Okay, so here in R1, what is an open set? Open set are the collection of intervals, right? So here in R1, here an open set. A, actually it is an element here in the topology. An open set A are the collection of the open intervals, right? So I mean, the union of is a union of open intervals. So A looks like, okay, you take the union of those open intervals. A finite union of those open intervals. It is open. What means open? That every point is an interior point. Right? In particular, you just think, in particular, an open interval is an open set. So in particular,
So any union of open intervals will be an open set?
yes.
That's just for the.
Yes, yes. Any union in, even the infinite union of open interval. Say, now how to define this open set? There are two kinds of definitions. One is its complement is closed. And the other is you can always find for any given point, you can always find the ball contained in that open set.
The neighborhood definition of
Yeah,
body.
yeah. So this is the ball center for any given x here, right? Given x here. So you have an r. R is the radius of the ball, r. So here, bx r, radius r is contained in A. Okay, and we call it open. Right? Open means every point is an interior point. So it's inside. You have no matter what point here, you can always find a small radius so that the whole open interval center at x is contained inside there. Right? So this is not in the set A, right? It is not in the set. But this is no longer true for a closed interval, right? Or half closed interval. Say you have an interval like from 0 to 1, it is closed, including the endpoint. Now the endpoint is not an interior point, right? You do not have a ball of radius r center at this point that totally contained inside the interval. Okay, so that is the boundary point, right? The boundary point is no longer true. So here, this is not open. This 0, 1 is not open, right? Not open. And instead here, this is 0, 1, this is 0, 1, this is open. Okay. And also half open is not open. This is not open, not open, not open. For an open set, every point is an interior point. Okay. That is surrounded by the point inside the set. Okay. So that is open. And then here we just generalize this to the topology, the collection of topology you think as a collection of open sets in this particular matrix. So here for every A in this topology, or you think as for every open set, then you can always find a ball for every point. So here the picture looks like, okay, so this is the set A. The set A, we say that it is open if and only if for any x in A, so you have a ball of radius r, center at the x, contained totally in A. No matter how close the point is to the boundary, right? Say if this is x, you can always find a smaller ball that is contained totally in A. Okay. So in one word, that every point is an interior point. It is surrounded by a point inside A. In the sense of the matrix. Okay. All right.
Okay, this is
So now-
R2.
No, this is any set. So not just R2, not just R3, Rn. It is any metric space. For example, so you may consider some, so even some discrete metric space. So since you are not so familiar with this, so let me maybe show you some examples. continuous function, the set of continuous function. Here is an example. Say if we let x be, our notation is CAB. So that is the collection of continuous functions on the closed interval. This is a collection of continuous functions. So each element is a function on the closed interval AB. Okay. And the topology is defined, and the distance, okay, the matrix defined to be DFG, right? So it's defined to be the distance between Fx and Gx. And we take the difference and then take the maximum value, x belongs to AB. Okay, so for any Fg belongs to x. Okay, and the distance. Okay, so intuitively the graph looks like, okay, say here we have an interval AB, we have continuous functions. So if this is a f, okay, this is a fx, the graph of f, and this is the graph of gx. Okay, this is g. Now, d is the maximum difference between the two. The maximum difference. So this is d infinity fg. Okay. This is take the difference and then take the maximum difference. Okay. So the maximum difference is the distance between the two functions. This is the graph of these functions. Yes. Yeah. Yeah.
So I'm just a little bit confused. Like, okay, so we're defining the distance, right? So, and we have f and g. So we're taking f of x and minus g of x, and we're maximizing that, and then we get an interval. We get that.
Yeah, that's
right.
right.
And that's the distance between what? Any two elements in the metric space.
Between this metric space.
In this metric space, right?
Yeah, in this metric space, under this matrix.
So that's the distance between any two elements in the metric space. So could elements be further, or no? They have to be that distance. It's like a discrete metric space with element and then that distance and then another element.
Now you have different metric space. I mean, this metric space under this matrix is defined like this. And then for different metric space, you may have different metric, right? Yeah, you may have different metrics. Even in this same metric space, you may define another matrix. Okay, you may even define another matrix. So our open interval that open set that refers to this matrix. Okay, to this matrix. So yeah, it's kind of difficult to change it from this one-dimensional to this infinite dimension. This is a space of infinite dimensions. Actually, okay. Each element is a function. It's a function. So the distance between f and g is measured like this. Okay. So for example, say okay, cosine x and gx. Let's show you an example. Okay. Say okay, AB here between 0 and pi, right? And then if we let fx to be sine x, and then let the gx to be cosine x. Okay. Now let's see what's the distance between the two functions. Now d infinity, right? Fg, which by definition is the maximum of the difference between sine x and cosine x. And that x belongs to 0 to pi, you take the maximum. Now let me draw a picture guys, to show you what's the maximum distance between that.
It's gonna be 2, right?
Yeah. So this is from 0 to pi, right? From 0 to pi. And the graph of sine looks like, this is pi over 2. The graph of sine that looks like this, right? Okay, this is graph of sine, y equals sine x. And the graph of cosine that looks like this.
So it's only
Okay.
1.
1, right? So the maximum distance. This is the maximum distance. This is maximum
That's also maximum technically.
I'm not sure whether this is the maximum. So, yeah, we, we need to calculate it may be more than one, okay. Let's see. It may be more than one. So in order to find the maximum, we need to use the so-called the method you learn in calculus 1, right? we take the derivative and then evaluate. So let's see. Okay, so if I let hx to be the difference between sine x and cosine x, right? Okay, and then let's see what is the maximum value of h, what is the minimum value of h. So we can take the derivative of h prime x, so that is cosine x, and then plus sine x, right? And then we let the derivative be 0. So we find the critical point, let the cosine x plus sine x equals 0. See, what is this x? Where cosine plus sine equals 0. How to solve this equation? Didn't solve this kind of equation. Cosine x equals minus sine x. Anyway, I will not ask you to solve this equation. It's kind of difficult. And then at the end point, the difference is 1, right? And then at the critical point, where cosine x plus sine x equals 0, let's see what is this. Okay. Yeah. At least we can plug this into here to calculate the value. So that is cosine x equals to minus sine x. There is another way. Without finding x, we will still be able to evaluate this and then plug into here. So that the hx is just 2 sine sine x plus sine x, right? Plus sine x. So that is 2 sine x. Okay. So at that point, okay, hx is 2 sine x. So 2 sine x is 2 sine x. So this is pi over 2. This is sine 2 sine 2 sine x. Anyway, the maximum. Anyway, the maximum may be 2. Yeah, so it's still not so clear what is the maximum. So it will take time to find out.
Don't we know that the maximum is 1? We just don't know if they're.
Yeah, the maximum is. Yeah, the maximum is what? Is 1. Yeah, the maximum is 1, but here we have 2, right? 2 sine x. So maybe sometimes maybe more than 1. I mean sine x maybe 1. So if it's still not clear, it will take time to find out what is this. Okay, this is what it is. But this is not important. At least we know that the difference. Yeah, at least the difference is at least 1. Okay. At least. At the least 1, so it's equal to 1, right? That's a good point. 1. Here the distance maybe we don't know. Yeah, it may require more calculation. Okay, but that is here just to explain what is the distance, okay, between F and G. So for this different distance, we will have a different topology, or the different sense of open set. So here, the ball of, so here in this, right? So in this xd infinity, now the ball of radius, the ball center at the A of radius r, and that is all the collection of the function f. So given, sorry, not A, I mean, this will be confused with the, now an element, let me call it f. An element is an f which is a point in this x. An element is an f. And then take f as the center. So we have a ball of radius r, center at the f. What that means? That is the collection of the element g in x, right, such that the distance, this d infinity distance of f and g is less than a. Sorry, no, sorry. Less than r is the radius. Okay. So that is, okay, here. All the element here, g. Okay. Now, if you come back to functions, then let me draw the picture, okay? So, if we, in the sense of function, now if we consider all the closed function on the interval AB, let me draw f, okay, say this is f. This is f. Okay. Then, what is the ball of radius r center at the f? So intuitively, okay, here let me just write this out. Okay, so that means the maximum value of the function between fx and gx, right, is less than r, maximum value. Okay, so here intuitively, if we draw on the graph of function, this is f minus r. This is fx minus r. This is fx plus r. I mean up there. Okay, let me. So this distance is r. This distance is r. Just move up and down here. So this is fx plus r. Okay. So what is the ball of radius r center at f? Which are all the functions, all the possible functions in between. So you draw randomly, draw any function. Okay. Any function. Okay, in between the two, right? So the difference between that function, the red function, and f is no more than r. Okay, the maximum value is no more than r. So that is to come back into the. But when we draw the graph of x, so this is x. X is collection. X is a collection of all continuous functions. Now each continuous function is just a point. Okay, and then this distance. Okay, in this space, it's just a point. So this is the difference is no more than r right here. Okay. So that is the ball. And then also there are discrete metric space where the matrix is defined differently. So here, this is another example. Okay, here, exercise 5.2.2. Here it says that show that this closed ball is always a closed set. So that this is a show. Now try to understand this concept more clearly. Okay, we show that first the concept of the ball, and then the close and the openness. That the closed ball. What means the closed ball? Okay, which is defined to be B-A-R bar. We put a bar up here. Okay, so that is defined to be all x belongs to x, and then the distance between x and a is less or equals r, and including where the distance equals to r. Okay. So let's show that this closed ball is always a closed set, is always a closed set in X. Okay. Now let me explain first by using one-dimensional picture. So first, okay, in one-dimensional, in R1, okay, we already know that, okay, this is the ball of radius R, center at A, right? So this, we have our notation that BAR is actually the open interval, A minus R to A plus R. This point is A minus R, this point is A plus R. The distance is less than R, right? Exactly less. Now, if you take the equal sign, right? If you take this dot up here, A, R, and that means include the equal sign where the distance equals to R. So that means including the two endpoints, right? A minus R, A plus R, but the close. Okay, so this is close. All right. Now, in general, okay, then of course in R1 this is closed, right? Closed interval is closed. But now in general, okay, in this metric space, how to prove that this is always a closed set? Okay, so you need to know how to prove that a set is a closed. What means a set is a closed? You take any sequence, right, in the set. If it converges, then the limit point must belong to it. Okay, all right. So what we need to use this definition to prove. Okay. So here to show that, so here is the proof. Now first, okay, let me put down, okay, let's recall that what means a closed set. Okay. Here, let's recall that closed set, the definition, we call that a set in the metric space XD is closed just in the usual sense. What means that you take every sequence, every convergent sequence, and the limit point must be in it. If for every sequence xn is a sequence in X, okay, such that the distance between xn and x naught goes to 0 as n goes to infinity. So that means this x naught is a limiting point. It's a limit point in the sense of this distance. Right? Then this x naught must belong to x. Right? Then x naught must belongs to x. So that means x is closed. Actually, this is if and only if and only if the definition. Right? You take a sequence of points which converges to some point, and then you show that this x naught must belong to the point. Okay. All right. So now let's prove this. Okay. It seems that at the beginning it seems that to be easy, but actually you need to use the definition. You need to strictly stick to this definition and the definition and the distance d. Right. All right. So let's start with the sequence. Okay. So here, so your proof goes like let xn be a sequence in X, okay, such that it converges, right? We try to show that this ball is this closed ball. I mean, including the boundary. Equal sign means include the boundary. the ball include the boundary, include the sphere, okay, not just the inside, is closed. So this sequence will be contained in B, A, R, Y. Okay? And that is,
So can you just repeat what it means for a set to be closed?
to be closed, right?
So
So if for every sequence, right, for every converging sequence,
okay,
the limit must be in the set,
okay,
and that is closed.
okay.
So this is not closed, right? This is open interval because we can take a sequence that approaches to the boundary, and this boundary point is not in, right? But this is, and then this is closed. The reason is that if you include the, all right, this is a minus r. This is a plus r. This is closed. Why? Because you take any sequence. Okay, now the limit is in. Okay.
But if it was open, then the
The
limit,
limit
could-
may not be in. The open, right? Then the limit of sequence. There is a limit. Of course, some limit may be in, but not all the limit is in.
Right.
Okay. So a closed set contains all the limit point. Okay. All the limit point is in, so that means closed. It is all closed. Okay. The sequence cannot go out. And it goes to a limit, and the limit is still in the set, in this interval. But here a sequence go here. All right, but this is not in the interval. Okay. The limit goes out. Okay. So we need to take a sequence that belongs to this by definition, right? So that means, what that means? That means the distance of xn and a is less or equals to r. Okay, by definition. And then also, we assume that this xn converges to x naught in the metric space xd. Okay. What that means? That means the distance between xn and x naught goes to 0. As n goes to infinity, right? Converges, okay? In the sense of d. Now, what we need to show is, we need to show that this x naught must be in, and then we want to show that this x naught must belongs to b bar ar. So that's it. Okay. So just like here on the picture that this is center A. If the set include the boundary, this is the distance r. And then if we have the sequence that converges to some point, okay, x naught may be here, then the sequence may go to the boundary, but the boundary is included. This boundary is included. Okay. Then this x naught has to be in the set. Then we say that the set is closed. Okay. How to show that this is belongs to this? Now the definition is, by definition, this is x naught, right? Maybe inside is maybe on the boundary. So that is what means by definition. This is the distance, right? The distance between A and x naught is less or equals to r. Okay, right? This is by definition of the set, right? This is our closed. All right. Now, actually, now it is not that difficult, right? So here we have. All right. We want to show this, right? So now we say that in fact, okay, in fact, what we use the triangle in equidistance A x naught. Okay. This, so, because we know that, we know this goes to 0. We also know that distance between xn and a is less or equals to r, right? So we will use triangle integral. This is less or equals to, we sandwich in distance a to xn plus the distance xn to x naught. Okay. This is less or equals to r. This goes to 0. Okay. All right. So this will go to because this goes to 0, goes to distance a xn, which is less or equals to r. No, I mean goes to, this is not rigorous. It changes. So anyway, this is less than r, this goes to 0. Okay.
So it goes to AX zero.
Huh?
It will go to AX zero. Oh, that's what it is. It just goes to
yeah.
R.
And this changes actually. So anyway, it is less or equals to r, this goes to 0. But this is not a rigorous argument. Let's use the Epsilon delta language to make it more rigorous. Okay. So so let me put here. Okay, so here, this we want to do like, okay, here we want to show that this is less than r. So I will erase this later. Okay. So here for any, we will show that for any epsilon greater than 0, this is less than r plus epsilon. So here, to be more precise, okay, here for any epsilon greater than 0. Okay. Now, all right, there exists, right? Because this goes to 0, so there exists capital N such that the distance between xn and x naught is less than epsilon for any n greater or equals to n. Okay. Hence, the distance between a and x naught, this is less or equals to the distance between a and xn plus the distance between xn and x naught by triangle inequality. Right? So that is less or equals to r plus epsilon. Okay, this is less or equals to r, this is less or equals to epsilon. So for any n greater or equals to n. Alright. Now you can conclude that because this is a fixed distance, right? So this is a fixed number since dAx naught is a fixed number. And then you show that a fixed number can be less or equals to r plus any epsilon. Right? Epsilon is any, so here epsilon can be any number. So this implies that the distance between a and x naught is less or equals to r. Okay. And that's the proof. Okay. To prove that something, this is a fixed number, then you prove that it is less or equals to r. You just show that you can make it be less or equals to r plus epsilon for any given epsilon. Okay, and you're done. All right. Now you prove that this is always a closed set in R. Right? But now be careful in the metric space. Usually in R1, then if we take the closed interval, and then if we take the closure of this open interval, the two should be the same, right? So here, let's recall that, but it is no longer true in vector space. So here recall that here in R1, okay, here let's just consider open interval. Okay, here if we take a open interval a minus r, a plus r. This in our notation is VAR, right? Center at A of radius R. And then if we take the closure, the closure. Let's recall that what means the closure. So this is the closed ball. This closure, what is the closure? That is the closure of BAR. Is BAR union or it's a limit point, right? So that BAR is this BAR union or is the limit point. And what that can be. So for a closed interval, right? I mean for an open interval. This is A minus R, this is A plus R. Okay. So of course every interior point is a limit point, but here also including the boundary. Right? So if an open set you include its boundary, then it becomes closed. Right? This becomes closed. So here the closure of BAR, we put it here, okay, in this notation, this is the closure. Okay. The closure of BAR. So it is the closed interval, right? A minus R, A plus R. Okay. And in our other notation, this B, we put a bar here. That means all the distance to the center is less or equals to R, right? So it is also, of course, also this closed interval, A plus R. Okay. So the closure of an open ball is the same as the closed ball. But in the metric space, this is no longer true. So let me show you an example. That is, in particular, this for the discrete metric space. Okay, let me use this. So, I mean, this will be one of the quiz questions, okay, for the next week. It's always the close. Yeah, sometimes the close or is always closed set, okay, in X, okay. All right.
Yeah, that's all right.
Anyway, some of this, anyway, you have copied. But now the next example shows that in particular in the discrete metric space, this the closure of the ball is always a subset, but sometimes maybe a proper subset. Okay. Here, this is exercise 5.2.3. So we show that in a metric space, and the metric space is X, D of X, okay, in particular, D of X, the closure of the ball just as I explained, the closure of the ball we denoted by BAR, put the bar here, okay, to show this is the difference between the closed ball. It's always a subset of the closed ball. You put the bar here, AR. So that is this B bar A R is always contained in VAR upper bar. But sometimes they may not be equal. Okay. So here sometimes the two. So here an example. I think it is better to. It's not so difficult to prove this is straightforward. But here is an example. Okay. So here sometimes the two are equal, right? Like this. Actually, in many cases, the two are equal. Okay. You take a closure and then take the closed ball. Only for some discrete set. Okay. Sometimes B bar A R may not be equals to B bar A R. Let me just show you an example. This example happens to the for a discrete set. Say, okay, if I just let the x to be what? To be okay, like minus 1/2, 0, and you can get many metric space, discrete ones. Okay. And then dx between x and y is just the absolute value, the usual absolute value between x and y. Okay. All right. I don't need this 1/2. I think this is B01. Oh, okay. This B01. All right. So now let's see. Okay, what is our B center at the 0, 1? Okay, the ball of the open ball. Okay. So we have this is discrete set. We have 5 points in the set. 0, minus 1, minus 1/2, 1/2, 1. Okay. So now the open ball. This point is not in open ball. The distance is 1, right? It is 1. The distance is less than 1. We have only 3 points. So that the open ball consists of minus 1/2, 0, 1/2. Right? Only 3 points. Then of course if you take closure, you still get the 3 points. Right? So B0, 1, if you take the closure. Because for the 3 point, the limit point is only the 3 point, right? And yourselves. We don't have this minus 1 and 1 are not the limit point of this because there is no sequence converters to these 2 points. So that is still minus 1/2, 0, 1/2. Right. But if we take the closed ball, closed ball are every point that has the distance to the origin is less than or equals to 1. Less than 1 equals to 1, less than 1 equals to 1. So it has 5 points in, right? All the points in. Minus 1/2, 0, 1/2, 1. Okay. The two are not equal. Okay. Alright, so I think it's the quiz time.
You can turn the video off.